All right. Once again, it gives me tremendous pleasure to introduce our next speaker. Not only is he an insanely amazing professor at this university in Pennsylvania, he's also a very, very talented musician, and some of you might have heard him playing the piano. That wasn't the tape, that was Bill Bahnfleth live. He is a past president of ASHRAE, and he's had probably the most difficult cat herding job in the world with this new standard, control of infectious aerosols. And he's going to tell us the how and the why the consensus was reached. Bill, take it away.
All right, yeah, thank you, Joe. Oh, mic is working. Always a great time to be at camp, and a tremendous honor to speak. And I wanted to speak again so badly. I wrote this got the standard written in 6 months. So that's worked so far. You know, if speaking right after lunch is a challenge, how about speaking right before open bar and dinner at Joe and Betsy's? I'll try not to hold you too long, but Joe did tell me I could speak for as long as I like. I'm imagining you'll let me know how long that is if we start getting past. So when I put this together, I thought to myself, how am I going to make a presentation about a standard into a typically funny, witty summer camp presentation? And that was it. So now we'll get on with the details here. So this standard is not even dry yet. It was published at the beginning of July, and one of the reasons for wanting to talk about it here is just so people would know about it, because I certainly have been living with it daily for a long time, so you kind of figure everybody knows what's going on, but I think this community and many others should know something about it, and maybe will help improve it and also apply it. All right, so control of infectious aerosols, it's an airborne infection risk mitigation standard, and you might well ask, why do we need one of those right now? I know I had that question when we started this, because I had other ideas about standards. If you were among the 60% of this group who were here last year, I talked about buildings and infection control and was thinking about, standards will change in the future. Well, events intervened. But so the reasons, airborne transmission of infections is important. We know that now after COVID. I was involved in some of those arguments with WHO through a group that was organized by Lydia Maraska from Australia. We know that the indoor environment contributes to risk of infection, and we don't have standards right now that address it unless we want to point to healthcare standards, and actually they don't do a very good job of it. We've come to learn by studying how their ventilation rates were determined. In a way, this is the completion and codification of work that we started in the ASHRAE Epidemic Task Force, which I stood up in March of 2020, which now seems a long time ago. We didn't go beyond guidance to things that could be stated as minimum requirements. And also, speed of ASHRAE. I think anyone's familiar with the ANSI code intended standards like 62.1 and 62.2 for acceptable indoor air quality. They move very slowly. And so it's not clear when or to what extent they might address infection risk mitigation. So that was another reason to do it. Oh yeah, and the White House came to ASHRAE and twisted the president's arm extremely hard to get it done, which was one of the main drivers. So quick chronology, the White House really started taking notice of buildings and their role in disease transmission late in 2021. This was already getting pretty far into the pandemic. And then by March of 2022, the White House rolled out a program called the Clean Air in Buildings Challenge, which was a voluntary kind of program, but at least gave some visibility to IAQ, and EPA is taking care of that right now. But then things got very interesting later in the year. I went to a meeting and talked about the need for a national model code for IAQ, and that was what really I was driving for. I spoke about it at a workshop that Johns Hopkins organized next to the White House in September. And then the White House itself had a summit a month later. And so these are the main points that I was making when I spoke at the Hopkins meeting, that incentives are great, like the Clean Air and Buildings Challenge, but a lot of times sticks work better than carrots. And we look at energy conservation, there's, I think, good history that shows that if you have a national standard and if it's adopted into law, as Standard 90.1 has been for non-residential buildings and with the IECC for residential buildings, that it causes some synergies that lead to a lot of progress that we won't bother reviewing here. And I think that energy conservation is going to remain the higher priority in most people's minds, but we can't allow it to drive bad decisions about IAQ. The buildings are for people, not for saving energy, as Bjorn Olesen, my former ASHRAE presidential colleague, likes to say. And standards need to be adopted into codes if they're going to be effective. So the point was that we ought to be getting some kind of national standard, but I was thinking comprehensively. So we go on. In November, the White House came to ASHRAE, and that's when they made this ask to develop a national pathogen control standard. I thought that was a great idea until they finished the sentence and said in 6 months. So they really wanted it to be in place by the time the COVID restrictions ended. I didn't realize that was actually the clock striking 12 for Cinderella, because at the end of that period, not only were the restrictions going to be lifted, but all those folks in the White House who were supporting indoor air quality and COVID response were going away. And so they're all back to their other jobs now. So in December of 22, the ASHRAE board said we'll do it, and we'll do it in 6 months. And then they went looking for someone dumb enough to lead the effort to develop it, and I raised my hand one more time. We did a call for members in December. In January, we got a roster approved and a title, purpose, and scope approved at the very end of the winter meeting. And we first started actually meeting to discuss the standard with the project committee on February 28th. We had a review draft by May 11th, 73 days later, did a 2-week public review, addressed 1,000 comments, and voted on a publication draft in the project committee on June 15th that was approved by the standards committee on June 24th. So it was 116 days of development time, which is probably 10% of what it takes to do a standard normally. So we're very pleased that we got it done at all, but we've got some nice feedback from Ashish Jha, who came to Tampa for the meeting where the standard was approved. And I won't read all of this nice stuff to you. You can find it on the ASHRAE website. But he noted in his remarks that it's one of the most important public health interventions he'd seen in decades. So I think this has the potential to be an important standard if it actually gets used. So now let's start talking about the standard itself, purpose and scope. Simply, the purpose is to reduce exposure to infectious aerosols indoors to reduce risk of disease transmission. And like many design standards, it applies to new buildings, existing buildings, major renovations, and covers that pretty comprehensively: design, installation, commissioning, operation, and maintenance. Now, the thing that concerns me about all of those standards is, though, that the part that gets adopted into the code is mainly just design and installation. So the operation piece of it is going to be a project for the future. And the way it works is by specifying a requirement that we call equivalent clean airflow, which is really a kind of revolutionary concept from the point of view of standards, because instead of simply having standards that talk about outdoor air, we're now combining all of the controls into one metric, and you can achieve that metric by different means, as I'll note. It's important to note that the standard does not establish overall requirements for acceptable air quality. You'll note there in the bullet above that it mentions infection risk management mode. What is that? That's when you need to use the provisions of the standard, which is something that needs further development, but I'll talk about that as well. And we say that it's limited to long-range transmission outside close proximity. That really means 3 to 6 feet, because it's just really hard to estimate the risk when you get closer by the methods that were used. So this is a list of the main topics that are in the standard. I think it would be familiar to you if you had looked at any air quality standard like 62.1 or 62.2, definitions, prerequisites, procedures for equivalent clean air flow, and then we get into assessment, planning, and implementation, which I think is actually a very important section as well, O&M. And because we were only writing one standard, we tried to shoehorn together non-residential, residential, and even healthcare buildings here. Healthcare is all integrated for the most part. There's one separate section on residential. So the key definitions that I'll talk about a little bit here, what is an infectious aerosol? What do we mean by air cleaning in this standard? Long-range transmission, which I've already touched on. Infection risk management mode in a little more detail. And the building readiness plan, which is a really important document that comes out of applying the standard. And finally, equivalent clean airflow, this thing that we want to achieve. So I won't beat this to death, but again, long-range transmission just means you're not in that radius around an infector where you're likely to get hit by droplet spray or be in their exhaled plume. So probably in the same room, but breathing a concentration of infectious aerosol at the average concentration of the room. So infectious aerosols are these collections of particles that are created whenever we exhale, speaking, singing, shouting, even just exhaling, and they have a known size distribution that's shown over here on the right-hand side. That it's kind of a bimodal distribution. We've got a lot of quite large droplets. These are the ones that fall out quickly, and then smaller ones that are down in the 10 micron and smaller range that are more likely to become particles that are airborne for a long time. So this is what we're really trying to control is those particles by various means. Air cleaning is anything we do besides dilution ventilation to reduce concentration. So it can be actually removing particles with some kind of air cleaner or inactivating them with technologies like the UV that you see in the room here. So mechanical filters, germicidal light, and reactive species all are possible ways of complying with this standard. I think we've gone a lot farther towards defining how that can be done. Want to note that the mention of specific technologies in the standard is not an endorsement. We're simply making it clear what kinds of things we're talking about. There is no ranking of controls in the standard. So infection risk management mode is a period when there's perceived to be enough risk that we would want to put additional controls in place. So that requires a decision maker to make that determination. Could be a public health official, so it could be something you're compelled to do. It could be a decision an owner makes. It could be the decision an occupant makes if we're talking about individual private homes. Why not use it all the time? Well, some of the things that you might want or need to do take a lot of extra energy, and one of the big issues that came up over and over again in the COVID guidance that was developed between 2020 and 2022 was, well, isn't that going to really derail my efforts to have an efficient building? So if you have something that's only used intermittently, that's going to help right a lot off the bat. And the other thing that we might note is that there are huge differences in the level of risk over time. Last year we were here, a lot of people were wearing masks. That's all pretty much gone away, and you see that most are living what they would consider their normal life without paying a lot of attention to COVID, even though people are still getting it. So those are reasons to have this be a special operating mode. It's an example, I think, of resilience in design of standards, which is an important concept that we need to consider for other things like wildfire smoke. Having the capability to respond to some kind of extreme event that hopefully doesn't happen all the time. So the Building Readiness Plan is a document that's prepared as the result of assessment and planning, and it documents all the things you're going to do to put the building into status to comply with Standard 241. And it's a direct descendant of what was called the Building Readiness Plan in the ASHRAE Epidemic Task Force guidance. So we've just beefed that up and turned it into enforceable standard language. But now to equivalent clean airflow, which I think is a really interesting thing. I've given you the whole definition here from the standard. Flow rate of pathogen-free air that, if distributed uniformly within the breathing zone, would have the same effect on infectious aerosol concentration as the sum of actual outdoor airflow, filtered airflow, and an activation of infectious aerosols. So it's kind of a conceptual airflow. If we were lowering concentration by dilution to a certain level with air cleaners or filters, we could replace that with an amount of uncontaminated air that would get to the same concentration. And once we've done that, now we can mix and match. So this is really the key concept of the entire standard, and we have tables there of what's called equivalent clean air for infection risk mitigation. And we use those values, which are per person values, to determine the requirements for spaces by multiplying by the population. And then the task becomes to figure out how best to achieve that target during infection risk mitigation mode. So here's a very simple example of how equivalent clean air works. In the upper figure here, we've got a space that has a source of some contaminant in it, S, and we're recirculating air through a filter that removes it with an efficiency eta at some flow rate QF. So we can analyze that system and figure out what the concentration is going to be. We can also imagine that we simply put air with a known concentration of the contaminant C0 through the space and then exhaust it an equal volume of air to maintain the same concentration. And we can show that for this case, the equivalent clean airflow is equal to the flow through the filter multiplied by the efficiency of the filter for that contaminant. And that's all there is to it. And we can add multiple sources of clean air together to meet the total. So we'll come back to this a bit more later, but let's now, before we go any farther, mention that there are prerequisites here that are important because this is not an indoor air quality standard. So it's built on top of the existing standards, and of course ASHRAE will say 62.1, 62.2, and 170, but it also notes in the details or other standard that is approved by the authority having jurisdiction, because this could be used in other countries, or there might be other reasons for doing that. So you've got to comply with the standard for ventilation and filtration minimums that you've always complied with. And so this is what sets the actual minimum outdoor air requirement for a facility that's using 241, and you don't have to exceed that. It's possible to comply with 241 without increasing the outdoor air at all. The only reason you would want to do that is if you determine that that's the most energy efficient and cost effective way, which might depend on your climate. All right, so there's a risk assessment that was done to determine these equivalent clean air targets for different types of spaces, and I think this is really totally unique in the standards world. If you go even to standard 170 for healthcare facilities, you find out that those air change rates are largely empirical from the mid-20th century, and that nobody knows what the actual risk is. You have a lot of decisions to make. When people asked us in the Epidemic Task Force, why aren't you putting out ventilation rates, this slide is why. Is it going to be absolute risk or relative risk? Am I going to try to reduce the risk by a certain fraction or to a certain specific level? How many infectors do I assume in the space? Do I assume that there is one there, which is a really stringent requirement, or do I use the population infection rate to determine what the probability is of having an infector there? How long is someone exposed? What is their activity level? And what controls do I assume to do it? So what you conclude in the end is that you need to use a probabilistic approach. Even if we take infector emission rate, someone has a different emission rate at the beginning of an infection, at their peak of infectivity, and later on. So the rate of emissions varies over orders of magnitude. So the method that was used was a Monte Carlo model where these different distributions of important distributed variables were sampled. And then we have to figure out what's the most appropriate unit. Equivalent clean air per person, per infector, or should we use air changes of ECA or something else? And unfortunately, everyone grabbed onto air changes because they're in healthcare standards early on in the pandemic, and nobody ever really looked very hard at whether that really made sense. And I'm going to try to clarify why air changes are not a very good metric and why we use infection or clean air per person. And there's a tiny amount of math here for those who appreciate math. I'll just try to talk through what this is showing. The equation at the top on the left is the Wells-Riley model, which is the one that's been used throughout the pandemic for estimating infection risk. So the probability of infection, P, which can be thought of as representing the number of new infections that will occur for a given number of susceptibles, so Ni over Ns, is a function of how much infectious aerosol is being put into the air measured in doses, in infectious doses. So the number of infectors multiplied by the quantum emission rate, and then how much air a susceptible person breathes, P times T. And both of those, if they get larger, increase probability of infection. The equivalent clean air delivery, Q, in the denominator makes it smaller. Now, if you consider that the concentrations of infectious aerosols are typically very small in the air, we can use a Taylor series. I didn't know that Stephanie was a mathematician, but it's very helpful. And so if you do that, you get P is approximately equal to IQPT over Q. So the exponential goes away, which makes things a lot simpler. So we're almost to the end here. If we include the population incidence of infection, which we did, then that's the number of infectors in a given space is going to be equal to the probability in the population, say 1%, 2%, multiplied by the number of people there. So I replace I with the number of susceptibles multiplied by the infection rate. And when I do that, I can show that the probability of infection is inversely proportional to the flow rate per person in the space. So this is all to get to P is proportional to Q over NS. So that's why we use that unit, because we want to limit the personal risk to a constant value. And you notice that air changes never show up here at all because they aren't really relevant. All right, so the risk assumptions we used in developing the standard, we used the Wells-Riley model, but in a much different way than you saw there, the statistical sampling approach. Number of infectors, a function of community infection rate, and what we did was to try to determine clean air flows that would give the same rate of infection or probability of infection per hour for any space, which initially caused some really logical questions about, well, your school day is 6 hours long, or I'm at the office for 8 hours. Don't you have to figure that out? And the answer is no, and I think this is one of the most brilliant things in this standard, is that if the risk is the same no matter what kind of space you're in, everyone is somewhere 24 hours a day, I think, right? So it doesn't matter whether I spent all day in school or all day with my parent at Take Your Kid to Work Day. You have the same probability based on the way we did this analysis. And the flow chart over there on the right, which you can read in the standard yourself, just shows how complex this model was to get to the ECAI values. All right, so what are the values and how do we figure out how to design these resilient systems for infection control? There's an excerpt from Table 5.1 on the right, which is like the table in 62.1 that gives you the ventilation rate per person and per unit area. And you can see the CFM per person and liters per second per person for different occupancy types there. And they're pretty big numbers. Even with all of these assumptions that we've made to keep them reasonable, they vary from 20 to 90 CFM per person. And so you take the appropriate number from that table and multiply it by the population in infection risk mitigation mode to get the flow for that space. I emphasize that because if you don't think you can produce enough clean air for your design population, you have the option, and it's easy to do with the standard in the form it is, to divide whatever clean air you can deliver by the amount per person, and you've now complied with the standard by changing the population. So it's very flexible method. Currently, we only have 25 space types and 7 categories. That's something we can work on. So how does 62.1 compare to 241 outdoor air versus ECAI? The numbers are a lot higher in 241. So it took office, classroom, and restaurants as an example, and the inputs from 62.1 are in the lower left-hand table. We've got to add together a rate per person multiplied by the number of occupants and a rate per unit area by the floor area. And so if I do that, we get and I divided by the number of occupants in a default space, we get 17, 13, and 10 CFM per person of outdoor air from 62.1 for office, classroom, and restaurant. We've got 30, 40, and 60 in 241. And maybe the interesting thing is here to finish my dismantling of air change rates is that the air change rates that correspond to our equal risk clean air delivery rates range from 1.1 to 31.5 in this example. So it really is not a very helpful way of describing airflow for infection control. There are other reasons to have air moving in a space, but not the clean air. All right, so how do we meet the target? We look at what we've already got in a building, ventilation rate, what kind of filters do we have, how much recirculation, and figure out how close we are to the target, and then evaluate different possible changes to get to that point in a way that meets all of our other constraints, cost and energy use, et cetera. So the user has a tremendous amount of flexibility here. The one limit that we've put in that maybe is kind of controversial is that first of all, we want MERV-A rated filters. For those who are familiar with the ASHRAE Standard 52.2 rating system, MERV-A means you've conditioned the filter to take the charge off of it before you test it. So the reason for doing that was that people do poor maintenance a lot of the time, and Electret filters, which work quite well when they're first installed, have the potential in some cases to really lose efficiency, and we just didn't think that was a safe thing to do. But there is a grace period until beginning of 2025 to do that. The calculations for equivalent clean air do get a little bit complicated. The figure on the right shows all the different places you can have an air cleaning system. There are 4 different distinct ones that result in different kinds of calculations, but we do have a tool to help with that I'll mention a little later. Standard addresses air distribution and natural ventilation, but really not to the extent that we want it to. This surprisingly turned out to be a very hard issue to address. We've got some classification of air cleaning systems, where they're located and what direction the flow discharges, but there really isn't a lot of research around yet to tell you how air cleaners producing the kinds of volumes you would have to have if they're, say, fan filter units, how they interact with the air distribution, whether it's mixing or whether it's stratified. So we've kicked that issue down the road. We're going to address it in the second version of the standard, but we need to do some work first. So mainly just some guidelines at this point. As far as natural ventilation, we've referred to what's in standard 62.1 about natural and mixed mode ventilation requirements, and we didn't do contaminant removal effectiveness or ventilation effectiveness, which really bothers the folks who do air distribution, because we know that's really important, how well air is distributed in the space. But you think about it this way: if you go to standard 62.1 and look for the credit you can take for having displacement ventilation for cooling, you get to reduce your outdoor air because that's supposed to be efficient. We've got UV in this space, and mixing actually makes it work better than displacement by a significant amount. So when we started seeing things like that, we thought, we don't really know what we're doing here and need to drop back and study it a little more. Really important section of the standard deals with air cleaning system effectiveness and safety. This is a new thing. Throughout the pandemic, we mostly just said kind of mealy-mouthed things like, we'll only use air cleaners for which evidence of effectiveness and safety is clear, because people were getting sued and we didn't have good tests for these things, and there might not have been evidence that something didn't work, but there wasn't evidence that it worked either. So the requirements here are the start of what I think will be a very useful development. Effectiveness just means how well does a technology remove or inactivate infectious aerosols. Safety, we're concerned about the direct emissions of an air cleaner. So there's some air cleaners that put ions or hydrogen peroxide gas or other oxidants into the air that have health effects at certain concentrations. And also we can have ozone produced by some of these air cleaners. Direct exposure to UV, if it's at too high an intensity, can have health effects. So we have some checks for that as well. That we had to get out in front of the whole air cleaner testing standards world to do that. We'd hoped that some standards that were under development would be finished, but we just went by them and they're still not out yet. So the standard is technology agnostic as far as air cleaners. It was our goal to not pick any winners here, but rather to establish requirements that would result in a level playing field. So we use some existing methods of test where they're applicable, like ASHRAE 52.2 for fiber filters, and 185.1 is a chamber test for UV, and the two AHAM tests, AC1 and AC5 for portable air cleaners. And we had to put a lot of these other procedures into normative appendix A, which is really our temporary standard until the other ones actually get published. They're under development. This is a list of all of the different types of air cleaning systems that need to be treated differently to some extent. We can have air cleaners that are in ducts that are classified by single pass efficiency. We have technologies like UV that act in a space, and all you can do is get a clean air delivery rate for them. And then we have mechanical filters for which we've had standards for a long time. So that's maybe one of the easiest prescriptive parts of the standard, is that you can go to a table in 241 and there is a table there by MERV rating of the estimated efficiency for removing infectious aerosol. So that puts together the efficiency of the filter and that particle size distribution that we looked at before. And these are like what was in Epidemic Task Force guidance, but a little more conservative. The values here tend to be a little lower than they were previously. If you have an air cleaner and it's rated by AHAM AC1, that's a particle test, not an infectious aerosol test. So there's a weighted average equation that you use to do that. So it averages out smoke, dust, and pollen 30%, 30%, 40%. Safety is we're just dipping our toe in the water here. There can be many different things in the air and lots of chemicals produced by chemical reaction. The ones that we're mainly concerned about are ozone, formaldehyde, and particles, and that's in part because those are contaminants that we know are not only prevalent but quite harmful. So we're trying to get a small list that might actually be measurable in a practical sense. Fan noise isn't actually regulated within the standard, but it has to be reported. This was something that came up a lot in the pandemic when people were making Corsi Rosenthal boxes and just using cheap box fans that maybe were 70, 80 dB on their high setting. So it at least has to be reported so that when you buy an air cleaner, you have some idea of whether you're going to be able to run it on the high fan speed. And UV in the occupied space needs to be measured. As it was here, I can report, and you're all safe. Bill Palmer will back me up on that. All right, so that's most of the technical requirements. I want to say just a little bit about assessment planning and implementation. This is what gets into the building readiness plan, and as I said, it comes out of some of our earlier guidance, and the big picture is it's applying commissioning, retro-commissioning procedures to systems that control infectious aerosols and culminates in the development of this plan. It also includes methodologies for doing assessing the requirement for additional clean air, and a lot of supporting tools here. There's an appendix that describes tracer particle tests to do in-place measurement of clean air delivery, checklists for items that should be commissioned, a template for developing a building readiness plan, a calculator that's the descendant of the equivalent outdoor air calculator from the Epidemic Task Force. So this is a spreadsheet that you can use to calculate those numbers, and some other items of guidance. This figure comes from the appendix on tracer particle tests, and those who've done these sorts of things will just see that this is a pull-down test that is used to determine what the equivalent clean air delivery rate is for the particles that you use in the test. This is the first page, or part of the first page, of the Building Readiness Plan template. Very easy to use, and it doesn't have to be a long document, just enough to meet your needs. And this is a sheet from the equivalent clean air calculator. So the blue items are from menus. So if you picked office, it would say 30 CFM per person, ECA. You put in the values for your space, and eventually it will tell you what CFM per person you actually have and whether it passes or fails. Section on operations deals with a number of important things, like keeping your building readiness plan on site and accessible and current, stocking supplies. And remember what happened when everyone needed more efficient filters at the beginning of the pandemic. They weren't to be found. Masks, for that matter, as well. I got my first batch of masks in 2020 from a friend in Beijing, which it turns out is where a lot of them are made. There's a real supply chain problem there because all of that had been sent out of the country. There are 3 operating modes that need to be defined: normal, occupied, non-occupied, infection risk management mode, occupied, non-occupied, and temporary shutdown. We've stuck with the statement that temperature and humidity set points should be maintained at design levels when occupied. There are requirements about occupancy schedules, basically that when there are people in the building, you have to be meeting the requirements of the standard. And because you will often lose a lot of air cleaning if the fan cycles off, if you're relying on the filters in your air handling unit, you can't have on-off control during this mode of operation either. And there are requirements for operator training and communication with occupants. Maintenance items are taken from ASHRAE ACA Standard 180. We've stated them again. Of course, nobody's really enforcing them in most buildings, but they are now there. And the main difference between 180 and 241 is that some items, like checking your outdoor airflow, have to be done more often, every year instead of every 5 years. And there are some special requirements for different types of air cleaning technologies. Here's the table that shows things that relate to air cleaning technologies, in-room air cleaners, UV, and in rooms. Right, so we're almost to the end of what's in the standard. The additional requirements for dwelling units are things that you may have heard of a long time ago, like having lids on toilets and keeping water and plumbing traps. That's actually pretty important in some types of multifamily buildings. Blocking airflow from where there are multiple units served by one system if there are vulnerable or infected occupants in some of the units. And because homes, like hospitals, healthcare facilities, are places where you may actually have to have someone infected present, we have a requirement for a separation area in a home, which could just be a bedroom with a door you can close so that someone can be isolated. We talked about depressurizing those. That may be something in the future. And if there's a vulnerable occupant, then the healthcare patient room ECAI is required for the whole dwelling. So what are we doing in the future? A lot of communication, like what I'm doing right now. There are articles being written and other presentations being planned, a web page, trying to get some pilot testing going soon so we actually get some experience from the field on how this works. This is not an ANSI standard. You don't develop an ANSI standard in 4 months. So that's another thing for the future. And as of now, we're moving forward following ANSI procedures in anticipation of doing that. Of course, trying to get adoption in codes eventually is another big job. And getting referencing in 62.1 and 62.2 is something else that we think is important. 62.2 is actually working on a continuous maintenance proposal. 62.1 has not budged yet as far as I know. So things that we may add under continuous maintenance, a performance path, so instead of having a prescriptive table that embodies all of the assumptions that we put into it, you maybe can come up with your own custom targets, somewhat like the indoor air quality procedure in 62.1. More explicit addressing of energy use in the standard, more space types, better coverage of air distribution, updates to air cleaning testing as new standards are coming online. So plenty of things to do. We're not going to start until the fall on that. Right now we're really doing some initial rollout stuff. So to wrap up here, it's a quick example of this ballroom. We did this fair amount of detail last year, and so we came back and did it again just to give an idea of what would happen if we applied 241 here. So here are the specs on the space, 6,380 square feet of floor area, volumes about 80,000 cubic feet, and per the owner, 464 occupants. That's what they told me at the front desk. I'm not sure if we're above or below that number today. And from ASHRAE Standard 62.1, if we assume a meeting room, general purpose meeting room at a conference center, 5 CFM per person and 0.06 CFM per square feet, which would give us a breathing zone ventilation requirement of 2,700. We have 3 rooftop units here, and I trust that the outdoor air intakes are open this year. We figured out that was a problem last time. They've been retrofitted with MERV 13 filters, which per the table I showed you is 70% efficient, and we were kind of guesstimating the supply air flow rate at 14,400 CFM. Lou Harriman, who unfortunately couldn't be here, did a lot of the groundwork on this, and I want to give him a shout out. I'm sorry that he's not with us this time. The outdoor air is 2880, so it complies with 62.1, and we have 11,520 CFM of recirculated air that can go through those MERV 13 filters. So to analyze now relative to 241, if we assume an auditorium being the closest space type, that's 50 CFM per person. If there are 464 occupants, that's 23,200 CFM of equivalent clean air. What do we have in the existing system? 2880 outdoor air and 8870 CFM of filtered recirculated air for a total of 11,750. So we're pretty far short here. We need another 11,450. or we reduce the occupancy to 235. We could do that, Joe. I don't want to pick, though. So what could we do to make things better to get that additional 11,450? 100% outdoor air is not going to help unless we replace the air handling unit. So that's not a good idea. And when you have a recirculating system and increase the percentage of outdoor air, you just reduce the amount of recirculation. So it's almost a zero-sum game. If we increase the filter efficiency all the way up to HEPA, it would get us to the same place, 14,400. So we need to do something else. In-room air cleaners could help. You see some Corsi Rosenthal boxes around here, but it takes a lot of box fans to get 11,000 CFM. I think we're a little bit short of that. So really about the only thing that seems practical is something like upper room UV, which we've got again here, 254 nanometer system. And if we look at the sizing of a system like that, just to go into the details a little more, we need 0.012 watts per cubic meter of UV power to get 20 air changes per hour of equivalent removal for tuberculosis, which is actually a pretty tough bug. Viruses like influenza and SARS-CoV-2 are much more susceptible. So that worked out to a little under 22 watts of UV output power. And with open fixtures, the ones that don't have louvers on them, you could probably do that for as little as 24 watts in here. So from the energy impact point of view, it's really quite small. And at 20 air changes per hour, that would be 25,000 CFM roughly of additional equivalent clean air, which is a lot more than we need, so that system could be downsized actually. Air cleaners, they could work, but I looked up some numbers and you're floating around 0.1 watts per CFM for peak fan power for a portable air cleaner. So we're talking about another kilowatt of plug load in here if you were going to get 11,000 CFM that way. Just to give you a refresher on how the system works here, this is a plan view, and we've got the 5 fixtures, the 3 across the back are on the bottom, and then the 2 in the corners here, and the blue here shows where we really have good coverage. So this has all been checked out by our friends who do UV. All right, so I've gotten to the end. It's been a long day. This is our new cat this year, our neighbor feral cat, Mr. Socks, who comes around to get fed a couple of times a day but won't let us pet him and hisses at us. And so now we can all go and eat and network, as Marvin and Boo were showing here. Thank you for your attention, and if there's time for questions, I'd be happy to hear some. It's 3:57.
That's a new jet plane, isn't it?
So, I have one question. Let us imagine that above this room is 14 more stories. Would those numbers change or not?
Oh, yeah, what we were looking at in my example was the number for just this space, right? So that was for this space. If we had another ballroom above this one, that's another 20,000 CFM for that space.
In my previous life, I was a pulmonary physician. One thing I want to do is commend you for your effort. You were given an impossible task because I think you were asked to do something that you really couldn't provide the answer to the question. And part of that is, I think this may be the only standard that I'm aware of where there's no easy way to measure what it is you want to control. Unless there's a surrogate that's been found for the COVID virus in an aerosol form to have any idea of what the concentration is in any point in a room for what you want to control.
Yeah, well, you have to piece things together, and admittedly, it's very messy, huge uncertainties, but we know something about the particle size distribution. We know something from influenza and also SARS-2 about the viral load distribution in those particles, and we know what the efficiency of filters is. I think the most difficult aspect of it is for technologies like UV. We lack a easy way of doing that.
Right, but the other thing here is, doesn't matter where the UV is if the distribution of flow is from one person to another. And I think the study that was retrospectively found from the Chinese restaurant, where the airflow was from one table to another table that I think was 30 or 40 feet away.
Yeah.
And, so that it's where you are in relation to someone that's infected that has more to do with than the total ventilation or the filtration or the EV, and that's not something you can control or measure.
Yeah, well, here we've got mixing ventilation, and this is something that's been studied before, the effectiveness of upper room UV. And the Chinese restaurant, the one in China, I think that there are different points of view on that. Hugo Lee and his team did an extensive study of that facility, and yes, where the air went was determined by there being mini splits along the wall that created a certain recirculation pattern, but it wasn't really being blown from person to person. They watched every second of the video from that restaurant to see if people were actually in close contact. And you have people who are behind the infector and people who are many feet away, all getting infected. So the air distribution is important there, and that's why we need to do more with it. But I think that has come, at least in a large part of the community, to be viewed as evidence of airborne transmission of the type that we're trying to control. What we aren't saying we have a good handle on is what does happen if Mark sneezes on his neighbor here.
Yeah, thank you very much for your service in terms of this work. And I guess one point that I'm wondering is you didn't really look at, your model assumed people were at least 1.5 meters away, right? So there's some risk of transmission of people being closer to each other. And it seems like you could do some kind of, get some idea of what that risk would be of transmission occurring in the room, and maybe potentially reduce the risk from recirculation down to that level and use that as a metric, because essentially you could fix one problem, but you're not fixing the overall problem. I don't know if you consider a framework like that.
What I would say is that, we say that we did the analysis based on long-range transmission. That doesn't mean that the controls you put in don't also reduce concentration within that radius that we're concerned about. And help may be on the way, right? CERN, working with WHO, has been developing a two-box model for infection that it has both a close range and a distant one, and that model should be out pretty soon. It's actually done, and I've seen it. And so we're looking for ways to improve the overall risk so we don't have to say this eventually.
All right, thanks. I'll ask a shitty question.
Sure.
So I want to appreciate the fact that you brought up P-traps, right? And so I wondered if you had thought at all about requiring trap primers in floor drains or anything of that nature, because, and also how you came to think of that and how much of a problem that form of infection is.
Yeah, well, it seems to be something that happens in places where you have these huge high-rise apartment buildings. I hear mostly that it's from South Korea, from Hong Kong. I think it's a great idea to maybe add some specific measures. Right now, we've just said there should be water in the trap, but if someone wants to write a continuous maintenance comment suggesting that we beef up the specifics, we could do that. Or we're looking at developing things like user manuals around this that would provide additional guidance on how to implement to meet that requirement. With a minimum standard, you want to say as little as possible about some of those details, but they're important details. Yeah.
Bill, great stuff. Not to be cynical, but I can see through this a rash of snake oil air sanitizing technologies being thrown out there into the marketplace. Was there any involvement from stakeholders in that, like EPA, which are always wrestling with antimicrobials versus antimicrobial devices versus unregulated application equipment?
Catherine Ratliff and Vito Alacqua were both on the project committee, and Vito was the chair of the safety group for air cleaning. So, you've got to accept the risk that if you enable, which is all we've done, the use of air cleaners, that manufacturers who have products that don't work are going to try to crash the standard. But what we're trying to do is progressively create tighter and tighter requirements for testing that are appropriate. So, if you've got something you can prove it works and is safe by those tests, then you're in. But I think that's an area we need to do a lot more work because of how little we know about the byproducts that some of these air cleaners produce. There's been a lot of flap lately about UVC photochemistry indoors. I think these are soluble problems. Thanks.
Hey, thanks. So my question is, did any of your thought process include a consideration of positive aspects of exchanging little biological things between us that improve our immune
Probiotic
system?
Environments?
Yeah, well, or other exhalates that are actually helping build each other's immune system.
Yeah, the short answer is no. We didn't consider that. I mean, that's obviously a developing field. And again, if someone has information that's strong enough that it would influence the further development of the standard, it would be good to know. But really, to me, I want 241 to go away, and I want it to be part of indoor air quality standards. That's one reason I didn't think it was that important to have an ANSI standard, because I had maybe misplaced confidence in 62.1 and 62.2 to take it on board. So eventually, I'd be happy to see it retired.
Well, seeing no further questions, a wonderful round of applause for Bill. I'd like to say it's officially over day one. See you all at the clubhouse and our place, or the rest of you tomorrow morning. So thank you very much.